Hi everyone. Our work is called DSTEP, Dynamic Spatiotemporal Pruning, and we're a group from SIRC, Samsung Israel Research and Development Center. Some background for this work. In the last decade, there has been significant improvement in the field of action recognition by applying deep learning. However, these methods require a large amount of computation. In order to reduce computation, previous work often focused on more efficient architectures, for example, MobileNet. Another option is to reduce the size of the models using pruning or network architecture search. Another direction, which is most relevant for our work, is dynamic inference. In these methods, the amount of computation is adapted to the input data. Here are some related works in the field of dynamic neural networks. In general, these are networks which adapt computation per input, typically using small policy networks. For example, in the shown figure, given an input feature map, a cheap policy network is used to decide which residual blocks can be skipped and therefore save computation. Another example is dynamic channel pruning, which was shown to work well for image classification. For videos, ADAF uses a dynamic method which uses both channel and temporal redundancy and was applied for action recognition. Here we present DSTEP, Dynamic Spatiotemporal Pruning, which is a new approach to use the spatial, temporal, and channel redundancies in videos in order to minimize computations. It is a simple and generic approach which can be used in different video tasks and network architectures. In our results, we show state-of-the-art trade-off between accuracy and flops on different action recognition datasets. This is our network architecture. We use two types of policy networks. The first is a special policy network, which produces a binary mask for regions which need to be computed in the output feature map. The second policy network is a temporal policy network, which works on the channel domain and decides if channels in the output features need to be computed, copied from previous frame, or completely skipped. The full flow is shown in the figure. Given the feature maps of two consecutive video frames, we first applied a special policy network for each frame. Then, following the multiplication with the binary mask, we summarized the input features from the two frames using global average pooling. These two vectors are the input to the temporal policy network, which decides which channels of the output should be computed, skipped, or reused. As our policy networks output discrete decisions, we have the problem of non-differentiable operators. Therefore, we use the Gumbel softmax trick, which has also been used in previous works. During training, we use the loss shown here, which includes three terms. The first is the task loss, which is the standard loss for classification. The second term is the sparsity loss, which aims to minimize the average flops per video clip. Finally, the third term is used to regularize the convergence of the policy networks and to avoid suboptimal results. This is a plot of the top 1 accuracy versus G-flops for different methods on the Something V2 dataset. As can be seen, different models trained with our approach achieve the same accuracy as state-of-the-art methods, such as TSM, with significant reduction in computation. Also, if we compare our different working points to other views, as shown in the enlarged box, we can achieve an improvement of around 2% in accuracy for the same flops, or reduce flops by around 50% without loss in accuracy. Results in more detail are in this table. First, for ResNet 18 on Something V2 dataset, we show that we're able to reduce computations to around 80% from TSM, which gives state-of-the-art results, without loss in accuracy. We also show that compared to Adafuse, we're able to save around 50% of computations with the same accuracy. Finally, when comparing to Adafuse with the ResNet 50 architecture, we also reduce computation significantly with only a moderate drop in accuracy of around 1%. We also perform comparison with other adaptive methods on different action recognition datasets. On the Jester dataset, we're able to reduce computation by around 50% compared to competing methods with same or even higher accuracy. Finally, on the Minikinetics dataset, we achieve comparable accuracy with significant reduction in flops. In the paper, we also provide an ablation study for the different modules in our network. First, we can see that adding the static temporal shift is critical for achieving high accuracy as it performs temporal modeling. Then, compared with Adafuse, which uses temporal and channel redundancy, by adding our spatial gating module, we achieve a better accuracy versus flops trade-off. Finally, we find that the best trade-off is achieved when combining all modules of our network, including static temporal shift for temporal modeling, and all policy networks to make use of spatial, temporal, and channel redundancy. Here we provide visualization of the spatial policy network outputs. We show in red the areas which required more compute and in blue regions which were mostly skipped. This shows that we focus our computations on image regions relevant for detecting the action. To conclude, we present a simple and efficient method for dynamic inference in videos. We show state-of-the-art trade-off between accuracy and compute on different action recognition datasets. For more details, please read our paper and visit our project page. Thank you.